Welcome to R-Online classes.
Density differences among solids, liquids, and gases are fundamental concepts in physics and chemistry that explain a lot about the behavior of materials in different states. Let's understand it more closely. Imagine a colossal iceberg, towering and majestic. It floats because its density is less than that of the surrounding water. But why do the densities of different states of matter vary? Take, for example, a balloon, an ice cube, and water vapor from a teapot. The balloon, filled with air or helium, is less dense than the surrounding atmosphere, which is why it floats. The ice cube, although solid, is less dense than liquid water due to the unique properties of water molecules, allowing it to float. And the water vapor? It's a gas, spreading out to fill the space, with its particles far apart, making it much less dense than the water in the teapot. Density tells us how tightly packed the particles are in a material. This simple statement holds the key to understanding why different materials behave the way they do. The formula for density, ρ equals mass over volume. This equation reveals that density, ρ, depends on the mass, m, of the substance and how much space it occupies, its volume, v. It's a fundamental concept that explains not just why icebergs float, but also why balloons rise and clouds drift across the sky. Different substances have varying densities, which is a measure of how much mass they contain in a given volume. Let's look at some examples. Aluminium has a density of 2.7 gram per cm cubed. Water, the standard for density, sits at 1 gram per cm cubed. Hydrogen gas, however, has a very low density of 0.000089 gram per cm cubed. This variation in density from solids to liquids to gases is fascinating because it shows how the arrangement of particles affects the overall density of a substance. However, it is important to remember that not all solids are denser than liquids. For example, wood, which is a solid, is less dense than water, allowing it to float. Knowing a substance's density is crucial because it helps determine whether it will float or sink in another substance. An object less dense than the surrounding liquid will float. Conversely, an object denser than the liquid it is in will sink. Since the densities are primarily affected by how particles are closely spaced, the density of substances changes when they also change state. For instance, water expands when it freezes, which is why ice is less dense than liquid water. As a substance heats up, its particles gain energy and move more, causing them to take up more space, and decreasing its density. Conversely, cooling a substance slows down its particles, causing them to occupy less space, and increasing its density. Solid gold, for example, is denser than its molten counterpart. At room temperature, gold has a density of 19.32 gram per cm cubed, but above its melting point, it drops to 17.19 gram per cm cubed. Now, let's take a closer look at the density of water in its different states. What do you notice? Ice, 0.9168 gram per cm cubed. Liquid water, 0.9971 gram per cm cubed. Water vapor, 0.000588 gram per cm cubed. Water is unique compared to other substances because it is less dense as a solid than as a liquid. This anomaly is due to the orientation of the hydrogen bonds as water freezes. Slightly positive hydrogen atoms are attracted to slightly negative oxygen atoms, forming a crystalline structure. In ice, each water molecule forms hydrogen bonds with 4 other water molecules. Consequently, water molecules in ice are pushed further apart compared to liquid water, resulting in a hexagonal structure in ice. The lower density of ice than liquid water explains why ice cubes and icebergs float. A recap: density tells us how tightly packed the particles are in a material. Generally, solids have the highest densities, while gases have the lowest. Density also changes when the state of a substance changes. As substances are heated, molecules move more and occupy more space, decreasing their overall density. Lastly, question to everyone: how does the anomalous expansion of water contribute to preserving aquatic life during extremely cold weather? If you enjoyed this video and learned something new, don't forget to hit that like button and subscribe to our online classes for more engaging educational content. Your support helps us create more videos like this one.